Hi everybody. The next section we're going to look at is least squares regression. And this can get to be a little computationally intensive, so I would strongly encourage you to use Excel or StatCrunch or something like that when you're doing the homework. So let's look at some of the objectives in this section. So the objectives will be to find the least squares regression line, and we'll talk about what that is here in just a minute, and how to use the line to make predictions, and then we'll interpret the slope and the y-intercept of the least squares regression line. And then lastly, we'll compute some of the squared residuals. So as far as finding an equation that describes linear related data, let's look at the following example data here. So here we got some data, and we've got the corresponding x and y coordinates of the data here, right? So this would be like the point 0, 5.8, 2, 5.9, etc. And we want to find a linear equation that relates x and y, right? So we want to come up with an equation that just sort of describes the points x and y by selecting 2 points and finding the equation of the line containing the points. Now this isn't really what we want to do. We'll see that there's a better way of doing this, but one way you could get sort of an approximation is, basically find the slope of the line and then plug it into the slope-intercept or point slope form, and then just solve the equation for y. So eventually you'll get that the line through the point 2, 5.7 and 6, 1.9 has a slope of negative 0.95 and has a y-intercept of 7.6, which hopefully you should be able to see if you were to plot that. Now again, this is not really what we want to do, because this may not give you the line of best fit, because it only goes through 2 data points. But here's a graph. And so what we can do is use this equation to predict certain values. Like, let's say we wanted to figure out, well, what would y be if x was equal to 3? Well, so you go over to 3 on the x-axis here and then see what height you would have on the line. Right, so not on the graph, so not this point, but the point itself on the line. So just plug in 3 into the equation, right, and you get about 4.75, which seems about right. I mean, right, so here's 3 and here's 5, right, so it's a little bit below 5. Now what we really want to do is find a sort of a prediction line or a least squared regression line that's a better fit than what we just looked at, because trying to find the line through 2 points, if you've got a bunch of points, that's really not going to be a very good fit. So what we're going to do is calculate what's known as the least squared regression line, sometimes called the trend line or the linear trend line. So one thing I should mention too is that the difference between the observed value of y and the predicted value of y based on the equation is called the residual. So we saw in the last example that 3 was assigned a height of 4.75 by the equation, but you can see that 3 was actually assigned a height of 5.2. So this distance between the point on the line and the actual data point itself is called a residual. We'll come back and talk about that later, but essentially, and I'm not going to talk about where the equation for the least squared regression line comes from, because you basically have to use calculus. But essentially what you do is you calculate the distance between this actual point and some point on your theoretical line, and you try to compute it in such a way that the distance between the line itself and the residuals, or the point itself, or in other words, the residuals are at a minimum. So basically you want to minimize the residuals squared, and you don't have to worry about that, but we'll use y with a little caret over it, which is sometimes pronounced y hat, as the symbol for the regression line. So the actual regression line itself is given by this equation: y hat equals b sub 1x plus b sub 0, where b sub 1 is the correlation coefficient we saw in 4.1 times the standard deviation of the y coordinates over the standard deviation of the x coordinates. That's the slope of your regression line. You can also calculate b1 using the formula on the margin in 210 below the historical note on Legendre. Legendre, incidentally, was one of the people that came up with this least squared regression line, in addition to the mathematician Gauss. And then the y coordinate, or the y-intercept, is the average of the y coordinates minus this b1 we just calculated times the average value of the x coordinates. And that's the y-intercept of the line. So x, just a couple things to note here. X bar is the sample mean, S sub x is the sample standard deviation, y bar is the sample mean, and S sub y is the sample standard deviation of the response variable y. So let's look at an example here. Let's go back to our drilling data that I think we looked at in a previous section here. But so the idea here is this is the amount of time in minutes it takes for a mining company or something to drill this many feet, right? And you can see that as they drill deeper, right, it takes longer and longer to drill to that depth. So what we want to do here is find the least squared regression line, predict the drilling time if the drill starts at 130 feet, etc. Right? So parts A, B, C, and D. So let's look at the least squared regression line here first. So this will be the least squared regression line. And again, you can just do this in Excel if you want, or StatCrunch. Again, if you do want to compute it by hand, it's a little bit nasty. I think I've got an example of how to do that under instructor videos if you want to do that, but I'm not going to require you to do that. So once you get your least squared regression line, if you want to predict, what will be the time to drill to a depth of 130 feet, just plug that into formula, and that gives you about time of about 0.35 minutes. And then it says the observed drilling time is 6.93, and so the predicted drilling time is given by this. The drill time of 6.93 feet is below average. And then here's your data that we had, and then this would be the equation of the regression line, right? And you can see that the regression line does have a positive slope, so it should slant up and to the right. And remember, this should be roughly where the line goes through the y-axis, right? So if you were to pull this down here, right, you would see it would go through there at about 5.5 something. Okay, so there's an example. I should mention too that the regression line will always go through x bar, y bar, so you can use that when you're drawing these. And if I do ask you to draw something like this on the exam, it doesn't have to be perfect, but if the line is slanting in, say, this direction as opposed to this direction, obviously something's wrong. Okay, so objective 2 is to interpret the slope and the y-intercept of the least squared regression line. So let's go ahead and take a look at that. So the slope and the y-intercept of the least squared regression line is, so the slope in this case is 0.0116. That means for each additional foot of depth, right, it will take the time to drill 5 feet increases by 0.0116 minutes on average. Right? The y-intercept is basically, well, in this case, I guess it's subject to interpretation, but is 0 a reasonable value for the explanatory variable? In other words, the x-coordinate was, would mean the drill depth is 0, so that doesn't really make sense, right? So the time to drill 5 feet then, when we begin drilling it at the surface of the Earth, is about 5.5273 minutes. One thing to worry about here is that if the least squared regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, we say that the researcher is working outside of the scope of the model. So again, the idea of a regression line or a trend line is to be able to make predictions about the future possibly, but the thing is, your line really only models the data that you have. So if you're going to make predictions far in the future, like if your x-axis is time, for example, right, you don't necessarily want to use the regression line to help you do that. Objective 3, we want to compute the sum of the squared residuals. So the, I don't know if there's really anything you'll have to worry about too much, but in order to illustrate the fact, remember the sum of the squared residuals for a least squared regression line is less than the sum of squared residuals for any other line. You can use the applet called regression by eye if you want. Again, not anything I'm going to require that you do. Okay, so that should wrap up that section. So the next thing we'll look at is section 4.3 on diagnostics on least squared regression lines. As usual, if you guys have questions or anything, let me know.